Okay, everyone, so today we're going to be talking about stellar spectra. Let's get right into exactly what we're going to be learning. So in this lesson, you're going to learn about the relationship between emission and absorption spectra for stars and their composition, and also how we use Cepheid variable stars, which are also known as standard candles, to measure distances to other galaxies, distant galaxies. So first, we've got to review a little bit about what emission and absorption spectra are. We talked about this a little bit in topic 7 and topic 12, but let's just refresh our memory here. So emission and absorption spectra are essentially kind of how we identify elements. So we can think about them as fingerprints. Each element has its own unique emission and absorption spectrum. And again, this is due to the quantized nature of electron energy levels. So electrons in an atom can only jump certain energy levels. The space between energy levels is not continuous, but quantized. So there are only certain allowable energy levels. And when these electrons jump down in energy levels, they emit a photon. And these photons have to be certain wavelengths. And we can measure those wavelengths and figure out exactly which wavelengths are allowed by that energy level drop. And these energy level drops are specific to certain atoms. So for example here, the picture shows us the hydrogen emission spectrum. So we can see we only have a few visible light spectrum lines here that are allowed. And the absorption spectra is a similar idea. It's just that the hydrogen will absorb light that is shot at it. And those dark lines tell you the wavelengths of light that are absorbed, which cause the electrons to jump up in energy levels. So let's see how this applies to what we're talking about. So when we used a spectrometer, again, a spectrometer is something that divides up the light from a source into different wavelengths. What we see is a continuous spectrum that is broken up by dark lines for any star. And these dark lines are the absorption lines. So we get this because the center of the star, it's hot and dense, and it produces this continuous spectrum, this continuous rainbow we can see here. And the outer layer of the star is cooler and less dense, and that layer absorbs these specific wavelengths. So again, similar to the hydrogen absorption spectrum, we can kind of see that there are certain wavelengths that are absorbed by the elements in the outer layer of the star. And this helps us tell what stars are made out of. It helps us figure out what composes the stars, which leads us here. So if you look at a graph of intensity versus wavelength for a given star, you can see dips in the intensity at given wavelengths. So if we look here, we can look at the star Vega, the blue line there, and we can see again our graph of intensity versus wavelength. And notice that there are distinct drops in intensity at certain given wavelengths. And these drops in intensity match with the hydrogen absorption spectrum, which then we can conclude it strongly suggests that the outer layer of Vega is composed almost entirely of hydrogen, because there's not really any other dips there that point to another absorption spectrum. So this is kind of how we can figure out composition of stars. This also tells us how to figure out composition of other celestial objects as well. So exoplanets, we can use this idea as well. The planets in our solar system, we've used this to find out what makes up the atmosphere of these planets, and other stars as well. We can use this to figure out the composition of other stars as well. And a lot of times, these compositions can be more complex, so it can be more difficult to figure out the compositions, but we can still get a general idea of what is makes up these objects in the sky. All right, next I want to talk about Cepheid variable stars. And these are stars that are extremely luminous. They're extremely bright, so they can be seen on Earth from a very large distance away. So this is a really great way to help us measure distant galaxies. And these stars are special in that they undergo periodic changes in luminosity. So they get brighter and then darker and brighter and darker in a periodic fashion like this. Notice the graph is not perfectly sinusoidal, right? The increase in brightness is quicker than the decrease in brightness, but it is still periodic. And these stars have already completed the hydrogen burning phase, so they are no longer burning hydrogen as their fuel in the fusion reactions inside. And these stars pulsate because the outer layers of the stars expand and then contract, expand and then contract. Essentially, the radiation pressure from the fusion reaction and the gravitational force are constantly overtaking one another and then balancing out, overtaking, balancing out, overtaking, balancing out. And we get this cycle that happens with their brightness. And this is really helpful for us in terms of figuring out distances. We're going to talk about why in a second. So these Cepheid variables are called standard candles, and this is because of a special relationship between the luminosity of these stars and the period of their pulsations. So in the 20th century, an astronomer, Henrietta Leavitt, discovered this relationship. So we can measure the luminosity based off of the period of these stars, and that helps us find the distance to the galaxies that these stars are in. So again, we can measure the brightness with a telescope, and then we can use the Cepheid star's period to find the luminosity. We can rearrange this equation here to find the distance, and that helps us find how far away these distant galaxies are. And again, the only reason we can see these stars so far away is because they're very, very luminous stars. And these stars are often referred to as standard candles because they're a standard in terms of helping us find distances to these distant galaxies. So that's all we have for today, talking about stellar spectra and Cepheid variables. Have a great day.